Great. Well, that's a fantastic overview and introduction to a very serious problem. And just reflecting on what Simon has said, it poses a lot of challenges, especially for on the policy side. But I'm going to talk more about the fundamental science and the science that I'm involved in, which is veterinary epidemiology. And I start off with this slightly challenging proposition that what has veterinary epidemiology ever done for us? And then the tagline, of course, is to say what the impact of epidemiological science is in helping us understand the patterns of the present and then obviously to plan for the future. So I guess before I speak about veterinary epidemiology, I need to convey a feeling for what it is. And essentially, we are interested in patterns and processes driving infection across animal populations. And you're less likely to see, what is this point? A veterinary epidemiologist looking like this and more likely looking at things like this and then ultimately generating models and inferences about the world to inform policy decision or understanding about underlying systems. And then from this, then we can derive understanding about quantifying risks and then ultimately forms an evidence base for other actors in society to work off of. So in reality, I think Simon has really illustrated this in quite well, but just to provide how does veterinary epidemiology ultimately impact on disease control? Well, we work with a whole host of different stakeholders to provide this evidence base. So for example, the stakeholders could be the state, and some specific questions perhaps around test performance. An epidemiologist might be able to ask questions around how do the commercial tests or emergent tests on the market, how did they perform? Farmers themselves might be interested in risk or biosecurity risk and how do we mitigate this risk. And then, of course, consumers, we're all consumers at a certain level, might be interested in asking questions about should we be worried about products on the market and the chains in which they're dependent upon. And within this type of framework, we obviously work at different types of spatial and political scales. And veterinary epidemiology is a very important science, obviously, for global eradication efforts, and the most successful being the rinderpest eradication effort, globally eradicated in part through the help of veterinary epidemiology, but obviously at national responses for emerging and important rapid response functions, for example, foot and mouth, but also informing on local conditions and coordination. And as Simon has already portrayed, science is really at the key to a lot of successful bovine tuberculosis eradication schemes at the global level. So as Simon alluded to, we have an interesting multi-host system on the island of Ireland and Britain and the UK. And essentially it's made up of two hosts. So we obviously are very aware of cattle, the primary host, but we also have this reservoir, which happens to be, in this context, the European badger, and perhaps also deer may be involved. And we have interactions between these species which can cause or facilitate transmission, and this could be direct through inhalation or indirect through the environment. And we also have intraspecific transmission within herds and across herds, and intraspecific going on within badger social groups and across populations. I suppose what should be pointed out here, which is slightly different to Simon's, was that sometimes we even have evidence that cattle can transmit to badgers. So inherently what we need to think about is an interlinked system. Both species, both hosts are passing to each other. And what we're interested in is, I suppose, characterizing these transmission events and looking at how can we cut the chains to ultimately break down this overall epidemiological system. And really we require evidence, and that's based on tools that we apply. And obviously then we're working with a whole host of other different types of scientists. So for example, I'm aware now that I keep pointing to one, and there's a whole host of people that are probably not seeing what I'm pointing to. So I'll try and mix this up a wee bit. But anyways, essentially we work with disease ecologists and environmental microbiologists to get an overall picture of how this ecosystem functions. So what are the actual tools within AFBI to try and address some of these questions and the evidence base to move forward? You see the word modelling quite a bit, and it's certainly a very large component of what we do. So this includes statistical modelling and also mathematical modelling. But we're very aware of spatial distributions and how space can be a very important part of eradication schemes. So we use GIS and geospatial modelling and then integrate these types of techniques in simulatory environments to ask what-if questions, to ask very, very difficult and challenging types of questions that are sometimes unethical or very expensive to do in the real world. And then we shouldn't really ignore the qualitative aspect, because obviously there's a whole host of qualitative questions that need to be answered around addressing this policy and difficult area. So I'm going to concentrate really on some of the fundamental and applied research that we've undertaken in around the last 3 years around these general themes using the tools. So for a start, Simon looked at movement networks, and I'm going to talk a little bit about that. Obviously, the wildlife aspect. Test evaluation is quite a core component of the research that we do. The variation in risk across herds, so the theme of chronic herds, but also co-infection. And I'm going to talk about each of these issues in turn. So to begin with, I suppose the program is fundamentally based on being able to identify infected animals. And for this, we need to think a little bit about the immune system of their hosts. And this is a general kind of model presented, much of the work done in AFBI in the early 2000s to characterize what's actually happening in terms of the immune response in cattle to bovine tuberculosis challenge, and then ultimately how we diagnose infection. So we're all aware, we should be all aware of the tuberculin test, and this has a kind of a profile in which, oh, it's gone too far, in which we have a slightly delayed reaction in terms of once an animal is exposed and infected before detection. And then there's also certain circumstances where animals may be missed, and you might be able to pick them up through antibody responses or serological responses. So for this piece of work, I'm going to concentrate on this end of the spectrum, so essentially animals that have been missed through regular antemortem tests, and then also these early responders who are very, very important to identify and take out of the system. So if we look at this somewhat hidden infection part of the population, we have undertaken some work where we evaluated some of the commercially available tests on the market, 2 in particular there, and we asked the questions, well, how well do they perform relative to antemortem tests, but also post-mortem confirmation? And obviously this is for the basis of policies going forward in terms of how do we identify and control disease within herds. And what we actually found was that while these tests had considerably high specificity, they exhibited variable and sometimes quite low sensitivity. So our ability to find these infected animals, especially in this cohort of animals that are not reacting to the 2 antemortem tests, was reasonably weak, to be honest. And at least in the cohorts we looked at, when we used the gamma interferon test and the skin test in parallel, there wasn't really an additional cohort that were being identified in terms of these serological tests. So some of this has been written up, and you can follow up there or discuss it at another point. Then looking at the other side of the spectrum, so these early responders are quite an important cohort, because obviously we want to, as quickly as possible, identify infection, take it out of those herds, and reduce the possibility of within-herd infection and dissemination of disease. So gamma interferon is obviously a very well-known test that is used within the program in Northern Ireland. And we asked the question, of the animals that are basically skin test negative but gamma interferon positive, do they harbour any future risk? Because right now, or at least up until recently, it was a choice of the farmer whether or not to retain these animals or not. And so we looked at about 1,000 gamma interferon positive animals within 235 herds in Northern Ireland, and we followed them up to 5 years and seen what was their future risk in terms of just within those herds. And these are already high risk herds. And relative to animals that were gamma interferon negative, they had 2.3 times the risk of future failure in terms of the skin test. So obviously this is a huge risk to the farmer, and as Simon was alluding to, it's in terms of recrudescence, it's going to be a major factor. But even in the shorter term, at 18 months, we found that 22.6% of gamma interferon positive animals were likely to break down during this 18-month period, relative to only 6.1% in high-risk herds. So this really is evidence for action and for informing on the debate. So another issue that can affect diagnosis is something called co-infection. So this is the principle whereby if you have multiple infections within the same host, it can ultimately affect your ability to detect through diagnostics, but it also on occasion can exacerbate infection, which essentially means you could increase transmission. So if you can imagine here a system like this where we have an endemic pathogen, something like Johne's disease, which some people might be familiar with, and if this interacts with the TB diagnostics in terms of the skin test or the lesion pathology, it could cause basically TB infection progression and spread or misdiagnosis, which ultimately has a negative impact on eradication efforts. And within this realm, we looked at 3 quite important endemic diseases within Northern Irish context. So that was BVD, liver fluke, and Johne's disease. So this was actually a really good opportunity for us to look at some of these endemic diseases as well, of course, just to highlight that. And we've got a number of publications arising on that to look at, for example, the spatial spread and distribution and risk of fluke across Northern Ireland, which is quite substantial, but also BVD, and this will follow in with partners like Animal Health and Welfare Northern Ireland. One of the interesting findings we did find in terms of co-infection was that animals that were co-infected with liver fluke were likely to give smaller TB lesions found at post-mortem using surveillance data, and also lower lesion counts. So this ultimately could affect our ability to confirm infection within reactor animals, which is obviously an issue within farming stakeholders, and it could ultimately affect it's undermining our trust in the skin test interpretation. In terms of Johne's disease, we did find an interaction there, which, just to remind everybody, that the skin test is a comparative test with an M. avian tuberculin used in it. So it's not all that unexpected to find that Johne's disease, which is caused by Mycobacterium avian paratuberculosis, has an interaction. And this piece of work suggested that animals that were exposed to MAP may have a higher risk of disclosing with TB lesions relative to non-reactors. So we followed that up because that was some basic evidence with additional data looking at, we looked at ELISA tests for Johne's disease in individual animals, and we matched them to their TB skin test. And what we did find, even though there's a huge variation, this is actually a significant result. And we found that animals that are Johne's disease positive tended to have different reaction sizes on the avian side relative to Johne's disease negative animals. So what does this mean ultimately? Ultimately, what's interesting here is that MAP probably affects TB diagnosis. So again, looking at the whole systems, we can't really look at these systems in isolation. So obviously, we're trying to detect infection, and as Simon alluded to, there is a potential reservoir infection within herds. And I suppose we need to think about how these herds or these animals could potentially spread or maintain infection across networks. So if we can think about movement of animals, so this is just an example, a snapshot of data, and this is some work from one of my PhD students at Queen's. And if you can think about all of these points being nodes within a network, and they're obviously herds or farms, and then each of these points can be connected to each other through edges, and these connected edges are usually trade or movement. We can start visualizing how this network actually works and operates at the spatial scale of Northern Ireland. And obviously then we can start looking into this network in terms of how, I suppose, modular, how many components are within it. This is very important when we think about, I suppose, eradicating pathogens, because if it's based on the movement of individual animals. And so AFBI is involved in visualizing and looking at these data and ultimately ask questions about these networks to support the evidence base. So this probably we're going to listen about big data later on. There's various interpretations of what big data actually means, but this is probably in the realm of big data. So some of our networks had over 20 million movements, for example, involving maybe 6 million cattle and across about 20,000 different nodes. So it's obviously a highly complex challenge in terms of computation. But some of the highlight, I suppose, results so far, this work is ongoing. We find that there is this type of distribution. So this is called a power law distribution, which essentially tells you that the vast majority of nodes have reasonably limited numbers of connections. But then we have this very long tail. And these nodes are particularly important to the structure of the of the population, because essentially they have very high connectivity and are allowed to maintain connections between this network. So I have this statement here, not all nodes are equal. So just high-level results from this work. What we have learned so far is that this network is incredibly robust. By robust, what I mean is that it's robust towards perturbation. So, for example, if you wanted to remove some of these nodes, or if you put strict restrictions on these nodes, the network still allows for connectivity across the whole branch of the network, essentially. And also, this network is incredibly dense. As Simon also alluded to, it sounds very similar actually to the Republic of Ireland, whereby there's a huge amount of movement of animals across this network, which is obviously problematic in terms of infectious disease control. And then in terms of identifying some of these key nodes in our networks, we find that markets, unsurprisingly, are very, very important in maintaining this. This work is ongoing. So as I said, we have a distribution, I suppose, in risk across herds. And what we see here is that actually the vast majority of reactors come from a reasonably small number of herds. So this is quite important to identify and to look into. So we term these chronic herds, and we want to address two questions in this particular problem within bovine TB, and that was, well, what are the risk factors that we can identify that are associated with these chronic herds? And also we wanted to apply some spatial and temporal analyses to say, well, can we identify any particular clusters, and what can we learn in terms of epidemiological insight from that? So to address the first question, yes, we can answer that there is significant spatial and temporal clusters, and some of these patterns are emergent that you wouldn't get from basic surveillance statistics, which is quite interesting. And then if some of you were here last year, you would have heard the talk by my colleague Robin Scouse, who undertakes a lot of genotypic analysis, so looking at the variation in genotypes. And these genotypes have very, very clear home ranges. And we can utilize both of these data together to say something about the likely transmission across the networks. And what we're able to say that a lot of these chronic herds also had a lot of strain diversity, and a lot of the strain diversity was coming out of home range. So essentially, we can start saying that chronic herds behave in a certain way and are obviously engaged in activities that potentially increase their risk. In terms of the individual risk factors, there's some previous work by colleagues here in Dara that have identified herd size, so larger herd size, increased risk. We identified that as well. Buying in of cattle, so again, back to the movement story is important. The local prevalence, which could indeed impact the local wildlife. And then having associated herds, so this idea that you have multiple packages of land across the landscape could potentially be implicated in these types of chronic herds. But I think importantly, the novel insights that we've gained is that not only the strain diversity is important, so that tells you something about the incursion of infection, but also particular strain types were associated with chronicity, which basically means there may be a phenotype, and we're doing ongoing work to say that perhaps not all strains are equal in terms of transmission. Interestingly, we did find some associations with underlying badger metrics of density. So generally speaking, you had an increased risk of TB where you had increased badger densities. However, it wasn't a particularly strong predictor of chronicity. So it's chronic herds may be less to do with the wildlife reservoir and maybe to do with, I suppose, the system more generally. So then moving on to the wildlife. So this is work that quite a bit of it, to be fair, has been done prior to my time in AFBI on wildlife, but I think it's still informative as to the work that AFBI does in this space. I'm going to talk about 3 different particular projects that I suppose form the evidence base for, I suppose, policy and interventions going forward. So Simon has kindly introduced the 4-area project already, a very large-scale, intensive removal program to try and get an underlying, I suppose, evidence base to see if culling had some effect in terms of risk to cattle. And what I did was I revisited these areas up to 10 years after the original intervention to see whether or not there was any residual effects. And very interestingly, wildlife interventions, you can still have measurable effects up to 10 years after removal. And then moving on from that, we were really interested to say, well, is risk uniform or is it spatially, I suppose, is there heterogeneity in terms of spatial risk? What we found here was actually TB in badgers. This is about 5,000 different badgers culled through activities in DAFM. And what we find is that there's huge significant variation in terms of risk, but a very wide distribution. But we also found that there was significant relationship between the local TB risk in cattle and the local TB risk in badgers. So this adds to epidemiological evidence that these two hosts are interlinked. And then ultimately, these types of raw data can help inform about, I suppose, tracing or tracking the dynamics of the epidemic over time. We found quite a significant decline in risk. And then, I think there's a very strong need for us to understand some basic ecological information about badger populations, because they themselves are very heterogeneous across time and space, with obvious implications in terms of disease management interventions. So this work, we had a look at badger movements, which is obviously a key parameter in understanding how disease could spread across the landscape. And what we found was that the vast majority of badgers, as expected, don't move very far. But then we have this long tail distribution where we have some individuals that move very long distances, and these could be key important animals in terms of disease spread within that host. But we also found that there was a relationship between the estimated badger density and how far and how frequently they move. So obviously this has important implications in terms of disease interventions like culling, for example. And I think there is quite a lot of opportunities for AFBI to work in that space in Northern Ireland to bolster up the evidence base there. So ultimately we can use those types of previous data and put them into simulations. And these simulations, for example, here, I worked with some colleagues in Wageningen to develop some models to come up with what-if scenarios. So what if we did nothing? How would infection? Well, infection would be maintained. What if we introduced culling at a time point, et cetera, et cetera? And this is quite a cost-effective way to give some evidence base as to what large-scale interventions might look like. And actually, interestingly, we're able to look at combination of different effects. Obviously, the long-term effects of culling badgers can be quite detrimental to the local population, but if we combine them with other different types of interventions, for example, vaccination, can we maintain infection to a low level that is sustainable? So I'm just going to wrap up here pretty much to talk about what's the future vision for veterinary epidemiology within AFBI. I clearly think that there is some very strong opportunities in terms of getting more from data that's already collected. Obviously, the advent of big data, and big not just in frequency, but obviously in terms of complexity, we should be utilising this space and across AFBI. More integration and continued integration of molecular epidemiology to get insights. And then obviously looking at mathematical and simulation models to try and help industry and help policy to say what interventions might work. I think there's a large opportunity and a need for disease ecology and management going forward within Northern Irish context, and not to mention that we have a considerable portfolio of interests in other pathogens that are very important. And suffice to say that we can't do this work in isolation in an ivory tower. We are very much embedded in a broader society with lots of different actors, as Simon has alluded to. So successful eradication is really going to be dependent on our interactions and our evidence base, through academia, obviously through peer-reviewed publications and high standard and high quality, but obviously interactions with farming unions, obviously to policy stakeholders, our veterinarian colleagues, industry, and then other stakeholders within society. And I'm going to leave it there, and I just would like to acknowledge all of the many collaborators that we interact with. Again, Northern Ireland is a small place, but we were very lucky to have very strong and profitable interactions and collaborations with people from around the world. And I'll leave it at that. Thank you very much.